Hello and welcome to this course, Classical Motion of a Single Particle. I am Professor Supratik Banerjee from IIT Kanpur, and in this course I welcome you to a venture where we will learn together very interesting features of classical mechanics related to the motion of a single particle or even a group of particles, a system of particles, an extended body, where the resultant motion can finally be represented by an effective single particle. Now, why in this course I am emphasizing on this single particle? Because many a times conceptually the single particle motion and the interaction of single particle with with different or diverse environment and entities are of prime importance in understanding various natural phenomena, starting from fluid dynamics, starting from engineering problems to the problems like solar physics, astrophysics, etc. Therefore, in this course we will always take care of the part that the specific entity or the separate individual entity of a single particle is always respected, and with respect to that we will see how different aspects of its motion can be studied using the known tools of classical mechanics. Now, I hope all of you know what classical mechanics is from your high schools, and of course, you all know maybe sometimes much more precise information than me in terms of Newton's laws, which are the fundamental pillar stone of classical mechanics, right. So, in this course there will be no attempt to learn to teach you all those Newton's laws and everything right from the scratch, but what I will try to say to build up a didactic approach to understand classical mechanics and also to understand how classical mechanics actually may serve as a gateway to general aspect of motion, general aspect of evolution, general aspect of physics, higher physics, etc. Okay. So, you all know also, I think, that quantum mechanics, you know particle physics, you know nanophysics, you know condensed matter physics, but if you really think, I think after this course, when the course will be over, you will have some feeling that classical mechanics is exactly sitting at the main entrance of every room. Wherever you want to go, you have to say hello to classical mechanics. With that hope, I am starting this course. For this course mainly I will follow very classical books like books of David Morin, books of Kleppner and Kolenko, and if you want I will sometimes also can tell some books over. If you send me some individual mails or something, I will write some books like reference books where you can see a lot of problems. You see that we start by emphasizing this word classical. So, classical means something what is not strange for us and what is traditional for us, what we can perceive, what we can feel without any problem. This is not really very abstract. Classical is something which is known already. We do not have to strain our brain to understand this. So, you see, and when we say that classical motion, this is the class of motion which we can imagine much more easily than any other thing. So, for example, if I say two rigid spherical balls, they are hitting each other, you can easily connect that. If I say a ball is hitting a bat, you can easily connect that. Okay. But also if I say that a particle is falling from some height and it hits the ground, you can relate that. If I say a particle is actually flowing on the surface of water, you can relate that, you can see that, because this comes from your everyday experience. That's the classical mechanics is all about. Okay. Now, you see that it does not say that classical mechanics will only include the motions which you can see. For example, if you want to model subatomic particles, but in terms of, or for example even atoms, molecules, okay, which nowadays we know they are not classical particles, but still you can see that you can always model, I mean, in the arena of classical mechanics by saying, sometimes we say, okay, one very popular field is kinetic theory of gases, where we say every gas molecule is like a hard sphere and they are colliding with each other elastically. All these things are just saying in order to make sure that you can picturize the model. Okay? That of course, you know that all these particles are not purely classical particle, and kinetic theory is just a very classical theory. It is a model, it is a very useful model, although far from reality. Now, of course, under certain conditions, when you know when the temperature is greater than certain temperature, then the classical approximations are useful enough. Okay. So, when we say classical motion, that means that we can perceive or we can imagine the motion. Okay. Then coming to another point, that when we are saying that classical motion, of course, we know classical mechanics. Now, although maybe every one of you who is following this course, you know, but still I want to say that mechanics is all about the study of motion, and classical mechanics is the study of known or motion, traditional or classical motions. Okay. So, you see, like classical motion, classical mechanics, these things are should be associated with common sense. If you cannot imagine or visualize the motion with common sense, then I cannot say it is that classical. Okay. So, for example, a very 0th level example should be, if one friend of yours just call you after a long time, suddenly you receive the call and you even do not know the whereabouts of that person. Of course, first thing you will say, what's up, how are you? But then the next question will be, where are you, what are you doing? Now, of course, what's up, how are you, these questions are very much subjective and really something very relevant to human I mean living organisms or human behavior or something, right. But if we just forget that question, these two next questions, the second and third, where are you and what are you doing? If you think carefully, you will see these actually constitutes the base of classical mechanics. Where are you means I am actually interested to know his position, what he or she is doing. I am interested to know the state of motion of that person. I mean, doing in a more literal sense. I mean, of course, we are saying that how he is doing, whether the person is in business or is without job, like this. But in a sense, you can, like generally, you can map that to this feeling that I am interested to know that whether there is a motion associated with this person or not. Okay. So, these two things are the building blocks of classical mechanics as well. When it is applied to a single particle, we say this is the classical mechanics of a single particle. Now, in mechanics, we have two parts. So, I now say mechanics, which is the study of motion, has two parts. So, classical, of course, because it consists of classical motions or the motions which we can imagine. So, mechanics, we have two things, one is kinematics, another is dynamics. Before going to that, I am just writing again. So, classical mechanics, I have two things. So, one is position, another is some act of motion or state, I would say. Okay. Now, whenever we are just trying to say at a time given, at a given time, at a given instant, time instant, we are trying to understand where the particle is situated and whether the particle has any inclination to move further or to change the state of its motion. For example, if it was in rest, it was trying to now move, it is now trying to move, or if it was moving, now it tries to be at rest, this type of things. You see, here I am not talking about any technical terms, just common sense, you see. So, those two things are sufficient to give us the information about this instantaneous state of motion of a particle, that means for a given time, and this constitutes the kinematics. But if I go to one step farther and ask that why is the state of motion what I can see, it is just exactly, now if you can make an analogy with to your conversation of your, with your friend, that if you, after when the person said that okay, you asked that what you were doing, then the person said, well, now I am jobless, I was doing a job, then you can say okay, thank you, bye. Instead of that, if you now say that why, what happened, you want an explanation, this part is analogical to understand or to try to explain the motion of a particle, and this constitutes the dynamics. So, for a dynamics I need something else other than position and the attempt of motion or attempt to motion or something of the particle, I need something else, okay? And that creates something which we know that is a force, okay? And that is why, so this is the part which basically comes through what we know as Newton's laws of motion. Before that, I am just trying to say another thing is that it is a very systematic approach to understand any motion, any evolution where something is changing. You see, we understand that if there is a possible movement associated with a single particle, of course with time the position will change or should change. Maybe sometimes it may not change, but in general I cannot say it is always fixed. Then there is no question of motion, then everything we should shut up. If I now say the position is changing, the second question is the act of motion, it is a constant or it is also changing. This is a very subtle question, and as we can see, what Newton said that actually dynamics comes due to the intrinsic reason of the assumption that that the motion, when only the state or the some act of motion, what I say here, changes with time, then only dynamics comes into play. Okay. Now, what is that position I can understand in a 3D coordinate system or in an n-dimensional space, you know the position is just given by a point. Okay. In a 3D space it is just a point with 3 coordinates, let us say x, y, z. Now, what is this some act of motion, some attempt, some effort of motion, I can also say some effect of motion, what is that? Newton did a lot of experiment. He also had in mind some experiments from Galileo of motion, some attempt, some effort of motion, I can also say some effect of motion, what is that? Newton did a lot of experiment. He also had in mind some experiments from Galileo, especially experiments related to the projectile motions. Nowadays you have a lot of resources on internet and you can actually check that in more details, and you can see that when Newton tried to reproduce some experiments of Galileo or did some new experiments with other colleagues, what he found that all the experiments are actually boiling down to two simple things. The first thing is that, let us say if you have a lighter particle and a heavier particle, that means you always can have a feeling of mass, although I have not here introduced it technically, a lighter particle and a heavier particle, and if you somehow make them fall from the same height, all of you know from Galileo's like how to say, Galileo's experiment, that after some height they will both have the same velocity if their initial velocities are same, right. So, then if you see that I can just get hit by the smaller particle with respect to the larger particle, of course, I will be badly, worsely injured by the heavier particle. Now, you can do an experiment, a new experiment, where you just take two particles of the same heaviness, okay, and then one you start from some distance h, another is 2h, and then you will see that the particle which is coming from with the same velocity, initial velocity, okay. Nowadays we know velocity, okay. Of course, here I am just trying to tell you the background of Newton's laws, okay. If you start from rest, actually that is the maybe the I mean the easiest thing to say. If both of them are starting from rest, then the one which is falling from 2h would hit me much more than the one which is falling from height h, okay. Then they compiled the two things to understand, okay, so it is the heaviness and the so called velocity, which is the rate of change of position with time, okay, combined gives an effect of movement. Then what about just make a quantity which is just the product of these two and call this as a quantity of motion. So, then they call this thing a quantity of motion and constitute m with x dot, okay. This is just the change of position, okay. I should in order to be like meticulous, I have to be I mean I have to mention here position is just the x vector. So, this is nothing but this one, if you want, this x vector which has the components x, y, z, okay. And then some act of motion, I can write that another vector which is p, okay. Then I can actually see that this p is simply related to this x by m and d dt of this x vector, okay. So, this is just something which we gain from experiments and experiences, okay. Now, you see, if you want to understand that how they are related, of course, I can write the first one. So, x, I can say that x d of dt is nothing but this p by m. I hope I have written it perfectly. So, this p is this, yes, this, and then the question is, if p changes, then what happens? As I said just some minutes before, that this will give you the fundamental answer of dynamics. So, for that we need the laws of Newton. Newton said in his laws two things. One is, if you do not disturb a particle from outside by any means, then a particle which is at rest at some given point, when you start watching it, it will retain its state of rest. If the particle was continuing with some velocity, let us say v at the time instant when you start watching it, okay, it would continue with another with the same velocity v with time and in a straight line, okay. So, that was the first law of Newton, and Newton, by this thing he wanted to characterize something very qualitatively, the external entity which is trying to change the state of motion of a particle, he called that force, okay. The second law, so the Newton's first law, I write N1L, is just a qualitative definition of force. Newton's second law gives some quantitative measurement, and some quantitative definition of second law in terms of this momentum. So, that law says that okay, I now state, and you cannot question because they are the laws, that if p changes with time, then this p dot or dp dt will be proportional to that f. Now, of course, if you write equal sign, there should be some constant beta, and if you can say that I can now choose a unit of f in such a manner that this beta becomes 1, so that I can forget it forever, and I can write dp dt is equal to f. Since dp dt is equal to f, I can now write here is this. Okay. These set of equations, these two equations, they are very interesting because they somehow introduce a concept which is very general in physics and in various fields like ecology, epidemiology, biology, okay, evolution. Okay. So, dynamical system. Why this is dynamical system? A dynamical system basically is consisting of two things. One is fields. Fields means if I give you some domain, some points, then some quantities, some variables which are well defined at every point of that domain is called a field. Okay. And if I can define a system of equations which are just mimicking or which are just describing the evolution of every field associated, then I have a dynamical system. Okay. Here you see this actually is a dynamical system if there is a condition, it is not a dynamical system if I can write this f with respect to f in function of p or x or t, then the point will be that I have, then I can, if I claim that classical mechanics is consisting of two fields, vector fields x and p, then the evolution of x is given by simply p by m, and evolution of p is given by another function which I call f, of course, which can be a function of x, p and t. Okay. So, you see this is a system of equations where you have actually one intrinsic independent variable, that is t, and x and p, they are two variables which are depending on t, of course, and also may depend on each other, and their coupled evolution equations are given by this. And that somehow helps us in understanding classical mechanics as a dynamical system. If this system, so if this dynamical, this f is something which contains of a variable which is not x, p or t, then I cannot call this as a complete dynamical system. Okay. So, in the next lecture we will try to understand more about Newton's law and the different cases of equations of motions in classical mechanics and how to solve them. Thank you.